All right. Thanks, Ali and Eric, for the kind invitation to speak here today. So my lab focuses on study of the human microbiome in health and disease. We've been involved in multiple different projects over the years. A central focus for us has been the relationship of the microbiome and nutrition. And when we started this direction, we thought a lot about what we should study. And after giving it a lot of thought, we decided to focus on blood glucose levels, and more specifically, changes in blood glucose levels after you eat a meal, what's called the post-meal or postprandial glucose response, because it's very critical for weight loss, weight management. It's also been shown over the years to be very relevant to prevention and management of diabetes, but also to cardiovascular disease, cancer, and numerous other diseases. And not less importantly, it's one of the only clinically informative markers that we can follow in nutrition in a continuous fashion using continuous glucose monitors, which have been mentioned here today. And so with that in mind, we initiated in Israel what we call the Personalized Nutrition Project, enrolled 1,000 participants, connected them to a continuous glucose monitor for 1 full week, during which we asked participants to log everything they eat on a mobile app that we developed. So at the end of the study, we had 50,000 blood glucose responses across this entire cohort to meals. Together with that, we also measured medical background and food frequency questionnaires, blood tests, body measures, and sampled the microbiome using both 16S and metagenomic sequencing. To give you a glimpse of what the data looks like, here's a CGM continuous glucose monitoring data for one participant. We're zooming in on one day. We can see how blood glucose levels rise after this participant ate either breakfast, lunch, or dinner. They rise to different levels after each meal, depending on what the participant had to eat. And we can take the area under the glucose curve as a single quantitative measure of that person's response to a meal. And we had 50,000 such measures in the study. So the first question that we asked is, how do different people respond when they eat exactly the same meal? So to do that, we actually provided all of the breakfast in the study, 7,000 different breakfasts, either bread with butter, or glucose given twice to each participant, consumed at the morning after the night fast. And the first remarkable finding from the study was that we saw that when the same person eats the same meal on different days, the response is highly reproducible. But when different people eat exactly the same meal, they have drastically different responses. And this is exemplified here for 4 participants anecdotally eating bread. You can see reproducible responses within a participant, but very different responses across participants. And we saw this for every single food we tested across this population. So we then asked what correlates with this variability, and we turned back to all the measures that we collected. And indeed, we found that multiple different measures in the blood and also various body measures correlated with the variability. But what was most novel in this study were many associations that we found between bacterial composition measured either by 16S or metagenomics and enrichment of specific bacterial pathways that correlated with this blood glucose variability. So we wanted to ask if we can take all these individual associations and somehow unify them into a single predictive model that would predict personalized blood glucose responses to meals. So we used a machine learning framework whereby we inserted all of the personal parameters, the clinical parameters, and the microbiome parameters, learned a gradient boosting decision tree, and evaluated its performance on meals of held out subjects. And we were very happy to see that this model could dramatically improve upon state of the art at the time, which was to use the amount of carbohydrates in a meal as a proxy for the predictor, which does have signal but is not very accurate. And with our model, we could explain up to 50% of the variability in people's response to meals. And we're also very happy to see that after completing this development of the algorithm, we profiled a new independent cohort of 100 participants and obtained the same level of accuracy. And so the final step in this study was then to ask whether we can actually then use this algorithm to design personalized diets for people that, at least in the short term, would balance their blood glucose levels. So we recruited 26 new participants, most of them pre-diabetic, and we randomized them into 2 arms. In each arm, participants received 2 diets designed by the algorithm, one which we call the good diet, a diet with meals in which the algorithm was supposed to predict meals that would not spike glucose levels, and then the other with exactly the same amount of calories for breakfast, lunch, dinners, and snacks, predict meals that would spike specifically for that person the blood glucose levels. So to show you that these diets are not the trivial ones you might think of, here are the two diets for one of the participants. And you can take a moment to see if you can guess for yourself which is the good diet and which the bad diet for this participant. As you look at this, you'll notice that it's not trivial to predict because they each contain foods like ice cream in one, chocolate in the other, that would probably not be prescribed by your average dietitian in a week that's supposed to balance blood glucose levels. So this study, if you had a moment to look, this study, of course, was done in Israel. So it had to be, you see the hummus here, it had to be the diet on the right, which was the good for this participant. And what I'll show you next is, we believe, the most remarkable result that came out of the study. I'll show you what happened when this participant followed both of these diets for one full week, and you'll see the continuous glucose monitor data. So this is this participant following that diet term predicted to be the bad one. You can see very clearly spikes in glucose levels, in fact reaching abnormally high levels after meals, indicating that this participant is indeed with prediabetes. And then this same participant, just 1 week later, exactly the same amount of calories for every single meal, the diet with the hummus, the pita, and the ice cream, achieves actually fully balanced, fully healthy blood glucose levels without even a single spike. And we saw this dramatic differences in most of this small cohort that we tested here, that dramatic differences in the ability of the good diet to lower blood glucose spikes. So this we published in the end of 2015. And of course, then a major question was then, which also Eric raised this morning, which is, what is the long-term clinical impact, or is there a long-term clinical impact to following these diets and lowering blood glucose spikes? So we were very curious about this question, and so for the past 2 years, my lab has been running a very extensive clinical trial. It's going to finish in the end of 2019, but I can share with you some unpublished pre-planned interim analysis results. So this is a study that we're doing on people with prediabetes, 200 participants, randomized into one of two arms, either receiving our algorithm diet or receiving the standard of care American Dietary Association diet, similar to a Mediterranean diet. And the primary outcomes in this study are the changes in both the average glucose levels and the spikes. So in more detail, after 1 month of profiling, the randomization occurs, and then there's a 6 months of dietary intervention, and then another 6 months of follow-up. What we're doing very uniquely in the study, I believe, for the first time, is we're actually tracking participants with CGMs throughout the entire duration of half a year of intervention, including also the profiling period when they're on their habitual diet. We also have some secondary metabolic endpoints, some exploratory endpoints in terms of changes in microbiome and the metabolomics. What else? So here's results for one participant. This is one participant in the algorithm diet arm. This is before the intervention. On the habitual diet of this participant, where you can clearly see many glucose spikes when this participant eats what he normally ate just before joining the study, which may also explain why this participant reached prediabetes levels. So then this same participant, when we track his glucose levels throughout an entire month, the first month of intervention, we can see that we can virtually eliminate all of the spikes in glucose levels. When we see across the entire half a year of intervention, you can see great reductions in the spikes. If we quantify that, we see that this participant on his habitual diet spent over 2.5 hours above the critical level of 150 milligrams per deciliter. On the algorithm diet for an entire duration of half a year, spends less than 5 minutes above this critical level. Here's another participant, again, the 1 month prior to our intervention, many spikes in glucose levels, and then a reduction in these spikes during the 6 months of intervention. Here's another participant and another one. And if we quantify this across 47 participants who completed 6 months in this preterm analysis, for the vast majority of them, we see dramatically different lowering of the algorithm diet of the glucose spikes. In contrast, if we look at the standard of care, this is the diet recommended by the American Dietary Association for people with prediabetes. We see that on the habitual diet, they have spikes in glucose levels, and also on the habitual diet, and then during the intervention. I believe that, especially in people with prediabetes, people have not really looked with this particular sensor throughout what happens on this diet. And here's another typical participant on the control diet. And if we compare the estimated effects on the average glucose levels from the CGM data, we do see some mild reduction on the ADA diet, but we see a much greater reduction overall across participants on the algorithm diet. And to put this in perspective, I'm going to add the 3 lines corresponding to the gold standard diabetes prevention program studied by the NIH of over 3,000 people, which had 3 arms, either a placebo do-nothing arm, metformin, the first-line drug in diabetes, and then a lifestyle which achieved the greatest effect. Lifestyle in the NIH actually included the ADA diet, but also caloric restriction and enhancement of physical activity. In our study, on purpose, we only modified the diet, yet only with the diet without caloric restriction, without enhancement of physical activity, we can see an over double effect to what the NIH study achieved on the lifestyle change. And if you think that this is a relatively modest change, the NIH study actually followed participants for 4 years, and they showed that this effect of the lifestyle as compared to placebo was sufficient to drive a 55% reduction in conversion of prediabetes to diabetes. So if we're getting an even larger effect only with diet, we're hopeful that this will also be the case for us. So just quickly summarizing this part of the talk, I showed you a very large study that we did on 1,000 participants demonstrating that people have very different blood glucose responses to meals, that an algorithm taking personal parameters and microbiome data into account can accurately predict these personalized responses, that diets that we prescribe based on this algorithm can successfully balance blood glucose levels. These findings were recently replicated by a study in the Mayo Clinic and also by the study from Mike Snyder's lab. And overall, we've tested so far thousands of different subjects. So, I'd like to switch gears a bit now and talk about another challenge in microbiome research, which is to demonstrate the causal effects of the microbiota on our health. So in the last few minutes of the talk, I want to tell you about 2 unpublished stories that we've been working on in this direction. So in the first, we reasoned that if perhaps we can go to move beyond association, if we could go deeper than just looking at the level of bacterial composition and identify perhaps genes and bacterial pathways associated with various disease states, then maybe that'll bring us closer to looking at mechanistic links. And so we developed an algorithm that improves the assignment of short metagenomic reads to individual bacteria, and that allows us now to examine across the entire genome of any one bacteria and across multiple people and search for regions that are either deleted or are amplified in a sufficiently large number of individuals. So these are structural variations at the level of bacterial genomes that live in our gut. And indeed, we identify thousands of these different structural variants, or SV regions, and they're found in dozens of virtually every single bacteria that we examine. And very interestingly, we find hundreds of different associations now at the level of these genes or bacterial pathways that are associated with various disease risk factors like BMI, body measures, and various glucose metabolism features. So to show you how this brings us closer to hypothesizing mechanistic effects for the microbiota, here's one example of one of these different associations. So this is a particular 30 kb region from one particular bug, Anaerostapes hadris. This region is deleted in roughly 40% of individuals in our cohort. And we find that the 60% of individuals in which this region is retained are on average more lean by about 15 pounds. They also have a lower BMI, lower body waist circumference, and higher HDL cholesterol. So on average, they are metabolically more healthy. And so we examined which genes lie in this 30 kb region. And we found that they, by and large, fall into 3 main pathways. The first is for inositol degradation. The second is for producing butyrate from inositol. And the third is various sugar transporters that feed into this pathway. And so we think that what this region does is to convert sugar or sugar alcohols from the gut environment eventually into butyrate. And butyrate is a short-chain fatty acid that in the literature is very well established in providing host benefits like reducing inflammation and improving overall metabolic health. And so we speculate that individuals in which this region of anaerostasis hydris is maintained are better able at producing butyrate, and that will provide some benefits to the host. That speculation, of course, needs to be demonstrated in further studies. Short of doing that, though, we did find independent validation for this in a Dutch cohort, also similarly sized cohorts, but very different population. This very same region is also deleted in about 40% of individuals in the Dutch population, and individuals that retain this region in the bug also have significantly lower BMI as compared to individuals without this region. So that was just one example of one particular region in one bug and its associations and how it can get us closer to hypothesizing specific mechanistic links by which the microbiome can affect our health. But as I mentioned, we have many, many more different associations linking specific substrates, enzymes, various metabolites that may be produced by gut bacteria, and different disease risk factors. This is coming out very soon and bringing us, I believe, closer to looking at mechanistic links of the microbiome. So in the final few minutes, I want to tell you about some other unpublished work that we did. So looking at another possible way by which the microbiota can causally affect our health, that can be by various metabolites that our microbiome may produce, which may eventually reach our blood circulation. So to look at that, we used mass spec based measurements of metabolites in serum, and we added that to the 1,000-person cohort that we had. And then we asked what determines levels of metabolites in the blood, and specifically we did that using out-of-sample predictions, because that, in our view, is the most stringent measure of success. So just to give you an example, let's say that we wanted to predict caffeine levels in the blood from diet data. So what we would do would be to develop a model that uses only dietary data and tries to predict caffeine levels in the blood, and then we would measure success by comparing the predictions of this model in held-out subjects to the actual measured levels of caffeine in the blood. So when you do this for caffeine, the model actually works very well in predicting caffeine levels without just from dietary data. You can inspect the model and ask which features are actually driving the predictions. And in this particular case, as you may expect, self-reported levels of coffee consumption is the most single dominant features that actually drives these predictions. Now, caffeine is just one example. So we built models for each of the 1,250 different metabolites that we measured, and we predicted them every time from 11 different groups, categories of different features, for a total of over 13,000 machine learning predictors of blood levels metabolites. So what was quite remarkable is that we obtained significant prediction for about 92% of the metabolites that we measure. We could predict their levels to varying degrees, but to a significant degree. The most dominant predictions came out of diet. So diet predicted the largest number of serum metabolites, but in second place came the gut microbiome. We also showed that these predictions actually are fairly robust, because we showed that they independently validate into different cohorts, these very same models. And now we can also go, and as we did with diet, we can investigate the microbiome-based models to gain insights on the particular bacteria that may actually underlie in each of these predictions. So this is a certain feature attribution framework that I don't have time to go into, but in a sense, we can see here on the x-axis are specific bacteria, specific species. On the y-axis are different metabolites, and colored entries represents the degree to which a particular bacteria was significant for predicting levels of a particular metabolite. So here's, for example, 4 different metabolites that were very accurately predicted by the model. We can now add this particular bacteria and see which bacteria predict the levels of these 2 metabolites at the top, which happen to be unknown metabolites, and at the bottom for 2 known metabolites. And the reason this is interesting is because if these bacteria actually causally determine the levels of these metabolites, then it means that by adding or removing specific bacteria, we actually now have a way to modulate levels of specific metabolites in the blood. So if you have disease-causing metabolites, then this can give us a path forward to developing microbiome-based therapeutics. And just to finish with a proof of principle example of this idea, here's one case where we extracted all of the metabolites that, according to our predictions, were actually either increased or decreased by consumption of whole wheat bread. And we found that when we do a dietary intervention where participants are given whole wheat bread to eat for 1 week, indeed, metabolites that we predicted would increase in the blood indeed increase. And this was very specific because when the same participants ate white bread and not whole wheat bread, the same metabolites did not increase in their levels. So with that, just summarizing this last part, I showed you that now we couple serum metabolites to our cohorts. We can obtain significant predictions for about 92% of the metabolites with diet and microbiome, each explaining hundreds of different levels of compounds. And we have we show replication in independent cohorts. And this is proof of concept demonstration. I showed you proof of concept demonstration, at least in the case of in case of a bread intervention, that these types of models may actually give us a path forward to how we can intervene either with diet or microbiome to modulate levels of metabolites in the blood that we care about. So with that, I will just put the acknowledgement slide and thank the many people in my lab and collaborators that did this amazing work, and thank you for your attention.